All righty. Hello and welcome everybody to the live OpenSSL webinar, working with X.509 keys and certificates with our own OpenSSL engineer, Viktor Dukhovni. My name is Kajal Subkota and I will be moderating this webinar. Victor, next slide, please. As a reminder to everyone, all attendees will be in listen-only mode. If you have any questions, please feel free to use the Q&A box or raise your hand to be unmuted if you'd like to ask the question live, as we will be hosting a Q&A session following the presentation. If you're experiencing any issues with seeing the presentation here, please make sure your Zoom is set to the full page settings. And as a reminder, this webinar is being recorded and will be made available on our YouTube channel shortly after this presentation. I invite everyone to follow us on Twitter at OpenSSL_, as well as all of our social medias on Facebook, LinkedIn, and anything else we may have. And feel free to email us at feedback, that's feedback@openssl.org if you have any additional questions. And now I'm going to hand it over to Victor for the technical presentation.
Thank you, Kajal. Okay, good morning. We're going to talk about X.509 certificates today, and in particular, about the tools that let you generate and look and copy them and manipulate them and so on. So we're going to generate some key pairs. We're going to learn what's in a certificate, how to generate one that's self-signed, how to generate a certificate signing request for a certification authority to sign, how to actually sign it using your own CA, looking at the certificate files and making sure that they have the right content, converting them back and forth to PKCS 12 format for Java applications or for end users to receive certificates and keys, and how to verify certificate chains. Okay, assumptions. It'll be extremely helpful if you have the OpenSSL software available to you already installed, or will do so soon. I assume very rudimentary familiarity with public key cryptography. Just so long as you know what a public-private key pair is, you're pretty much in good shape. I do assume that you will have access to a bash-compatible shell if you want to try the examples yourself, and I strongly encourage you to try them, because I'll be racing through this to show you as much of the tooling as I can, but you'll really get maximal value from this presentation if you try many of the examples yourself, look at the documentation, and try variants on the commands that I've shown in the slides. You'll have the slide deck available to you sometime early next week, so please try the exercises as well. On macOS, the terminal application will be fine for running the bash stuff. Linux, of course, and on Windows, you can do this as part of the Windows system for Linux too. So you shouldn't have too much trouble finding yourself a shell in which you can try the examples exactly as shown. Okay, key pairs. We can't have certificates before we have keys. So in this slide, I'm showing 3 different ways to generate a key for that you might then wrap a certificate around. The first example shows how to generate an RSA key. It happens to have 2048 bits. It's a fairly popular key size for RSA. There's not much point in going a lot larger. The second example shows generating an elliptic curve key for the prime 256v1 curve, otherwise known as NIST P256 or SEC P256R1. It has lots of different names. In OpenSSL, for historical reasons, we call it prime 256v1. And the third command does the same thing with an X.509 key, but this time a little bit of extra effort in the shell goes to make sure that we create the file atomically. We create a temporary file first, write the key to the temporary file, and if all went well, rename the temporary file to the file where we actually expect to find the key. In carefully written scripts, you might use this third approach of writing key material to and various other things that you're generating automatically in scripts to temporary files, and only then putting them into place once everything went well. Private key files created by the genp command are automatically created, not world readable. Of course, unless the file is already there and has the wrong permissions, then it will be written to as it is. So it's another reason to write the files atomically, is that then you'll be sure that the files have the right permissions. I also want to note that if you're writing C code to create keys, then the responsibility for ensuring the file permissions is yours. The library isn't in the business of setting the file permissions for you. Homework, there'll be lots of these little homework notes at the base of lots of slides. Try variations, try other key sizes for RSA, different curves for elliptic curves. Right, in your own scripts, try this atomic update approach. Okay. The outputs of many of the OpenSSL commands are written in a file format called PEM. PEM files are largely human readable. At least you can tell what kind of thing is in them. And PEM files can hold or sort of a number of different or repeated variants of the same object. In this case, the first command here, OpenSSL rec-new-x509, creates a very simple, minimal self-signed certificate. And we're using the L25519 key as the key that the certificate is wrapped around, and we're appending it to the key file. So now the key file has both the private key and the certificate all in the one file, and it's a PEM file. So if we look at it, we'll see that it's got both a private key and a certificate, and which one of those you see depends on which command you use. If you use the OpenSSL pkey command that works with public and private keys, it will look at the key in the file. If, on the other hand, you use the OpenSSL X.509 command that reads the first certificate in the file, it will then see the certificate that we appended. But the file really has both. The tool determines what's of interest. The other format that you'll see often used with certificates is called DIR. Stands for Distinguished Encoding Rules, and it encodes a single ASM.1 object. ASM.1, syntax for serializing data structures, part of the OSI stack from the 80s and 90s. The D, as I mentioned, distinguished, means that there's really a single well-defined way of encoding every object. And this is useful when you're signing things or computing their hashes. You really want to make sure that they're in standard form. So DIR is the preferred binary format of all of these data, and PEM is a base64 encoding that's more human readable and supports multiple things in the same file. In DIR form, you'll often see in Windows.cer or .crt when it's a certificate. There are various other objects that are in DIR form, and they tend to have separate file extensions in Windows, sometimes .p12, sometimes various others. Homework, play with converting things to and from DIR formats. We'll see how that's done in a moment. Okay. I keep mentioning this word certificate. What is one of those? So a certificate, we're going to look at what's in them. We're going to talk about names. We're going to talk about the different types of certificates. And we're going to be creating a certificate signing request with a particular choice of DNS names in them, which is the most widely used certificate type is for DNS naming. Okay. So a certificate fundamentally by design is a way of assigning a name to the party that's supposed to be the sole holder of a private key. So when we run the OpenSSL X.509 command and give it a file with a certificate to read, and we give it the -text option to decode the certificate in a human-friendly way rather than just present the base64 encoding, then what we see is that it's got an issuer, a validity, a subject, and it's got the public key. The issuer and the subject are blank here. We'll talk about that in a moment. But the validity specifies an expiration date for the certificate. The inception date, the not before date, is of course usually in the past. Well, of course, it's possible to future date a certificate, but that's rarely done. And the public key consists of the algorithm and then the key data. And sometimes there are additional parameters for the key, although not relevant here. The subject public key info is the combination of the algorithm and the key data together is called the subject public key info, or SPKI. You'll see that phrase thrown about a lot, or that abbreviation thrown about a lot. I'm not showing you everything that's in a certificate. There's a signature and version and so on. In fact, the full content of a certificate here, the cyan bits are the required standard fields. So every certificate will have a version number, a serial number, an algorithm ID, issuer validity, all of that good stuff. Then ultimately, most certificates these days have some extensions. So the extensions are important, but they weren't part of the original specification. They were introduced later, but are now essential ingredients in every certificate. The authority key identifier and subject key identifier are also extensions and not something else, but they're important ones that we'll cover next. And finally, the certificate is signed by its issuer. The signature covers all of those other fields, including the extensions. Okay, so extensions. Certification authorities, or CAs, have certificates of their own, and those certificates will have at least a few important fields that to keep track of. The subject and authority key identifier are useful when building certificate chains. The signer will usually copy his subject key identifier into the certificates that are created, and it'll become the authority key identifier in the created certificates. And this lets you chain the certificates together. So when you see a certificate whose authority key identifier has particular data, you're then looking for an issuer with matching data for his subject key identifier. So these provide certificate linkage, and they're important to understand and track. The basic constraints for a certification authority should always have CA equals true. And if you're not a CA, you should really have a certificate whose basic constraints say CA equals false. And finally, I'm showing here a key usage. A certification authority will usually indicate in its key usage that it's supposed to be able to sign certificates and sign certificate revocation lists. Other key usages are available, and some of those may also be present in some certification authority certificates, but those are the two most important ones. A certificate, again, I mentioned, is self-signed when the subject key ID is equal to the authority key identifier. Otherwise, it's presumably issued by some other CA. Okay, names. So in the previous slide, the names were blank. But here, the subject is the key holder, and the issuer is the certification authority that issued the certificate. These names are X500 names, but there is no X500 directory, at least not a global one. And so the subject names in certificates that are ultimately used by application, pro servers and users in the end entity certificates, those subject names don't really have anything particularly important in them. They're somewhat obsolete and can even be left empty. But the issuer name in a certificate that's not one of these self-signed ones that has no names at all must not be empty. So if you're going to operate a certification authority, it must have a non-empty name. Absent a global directory, these issuer names that were supposed to form some sort of hierarchy for the global X500 directory aren't really important so long as they're unique. So they should probably have some sort of name that means something to you, but what exactly it holds is not terribly important, just so long as you don't have multiple issuers with the same name that are unrelated. So if the subject name is blank, but the certificate is supposed to tell us who the key holder is, what in the world are we doing with these blank subject names? And the point is that these days, the real names in the certificate are not in the subject name, they're in extensions. And the extension that carries the names that you really want to bind to the key holder is the subject alternative name extension. And these are typed. They contain either DNS names or email addresses or IP addresses or URIs, and the type of the name is part of the name and then has the name value together in the subject alternative name extension, and we'll be seeing those in action in a moment. Okay, certificate types. There are 3 certificate types of interest. And entity certificates hold public keys that you get things done with. You're a web server, you're a web client, you're a signer, code signer, you're a time service. Any one of those things are applications that the server or client may have a key for, and it will have an end entity certificate to take that role. When expressly not a certification authority, it's good practice to set the basic constraints in a certificate to explicitly say that yes, it's not a CA. You can leave that out, and if the certificate is not self-issued and it doesn't have CA true, it's kind of implicitly sort of CA false, but it's best to spell that out in every certificate. Certification authority certificates can be one of a couple of different types: self-signed or root CAs or trust anchors. These are not issued by anybody else. They anchor the trust hierarchy for certification chain. Subsidiary, intermediate, or cross, those are all equivalent name certificates. They're issued to another CA by a parent CA, delegating its role for signing certificates to some operational authority. Sometimes that's done for security reasons. Maybe the trust anchor CA is kept in secure storage offline, used very rarely, and accessed by very few individuals. And its job is only to issue intermediate certificates, and those then do all the real work of issuing certificates to end users. So certification authority certificates, they should have basic constraint CA true, and they'll typically have, as I mentioned, these key cert sign, CRL sign, key usage extension. A self-signed certificate has same issuer and subject name and non-empty. If it's a CA, it really should be non-empty. And when those extensions are present, they usually should be there. They'll have matching subject and authority key identifiers. And of course, to be self-signed, you actually need to have used the same key to sign a certificate that it has in it as the public key of the key holder. So a certificate encapsulates the public key, and if it's signed by the private key corresponding to the public key, then it's really self-signed. Homework: does your certificate store have any certificates that are not self-signed? Sometimes that's true, sometimes false. Check it out, figure out which is the case on your end. Extended key usage also appears in certificates. This is specified by the standards to really have meaning pretty much only in end entity certificates. But OpenSSL and a few other implementations interpret EKUs that may appear in a certification authority certificate to also restrict what kind of certificates the CA can issue. This goes beyond the specifications, but is widely practiced. So for example, if a certification authority certificate specified that its extended key usage is server authentication, then that CA would only be trusted to issue TLS server certificates and wouldn't be trusted to issue client certificates or email certificates or anything else like that. Okay, now that we've talked a lot about what certificates can and can't do, let's actually build some. So creating certificate requests. So we're going to create certificate requests with names that are DNS names, the names of web servers, possibly the names of client systems as well. Similar things apply to email certificates and the like, but we'll focus on DNS here. So I'm creating a certificate signing request for an end entity. I'm giving it an X.509 key and an empty subject name. The --/ makes it just the root of the name list is, and then nothing else follows. So that makes this sequence of names empty. But I'm giving it an extension. Subject alt name is what we call SANS inside the OpenSSL tooling. And I'm giving it this comma-separated list of DNS names as the value to put in a subject alternative name extension. And I'm also specifying the key usage to be server auth. So this means that this end entity certificate is intended for some sort of web server. Or actually TLS server. It could be an email server as well, anything that terminates in a SSL connection. So we've created a certificate signing request, or CSR, creating a new one. That's what the -new thing is called. And we're specifying which key we're going to extract the public key from. We need both the public and private key because certificate signing requests are signed by the same key that gets embedded, whose public part is embedded in them. We can look at the certificate signing request with the OpenSSL rec command. And I'm not showing you all of the output, but I'm showing you the essential parts, empty subject. It's got the public key information in it, and it's got the extensions that we asked for, in particular, the two DNS names and the requested key usage of TLS web server authentication, otherwise shortly known as server auth. By the way, those DNS names aren't there as a comma-separated string. It's really stored as a sequence of names encoded in some binary format inside the certificate. Okay, so we have a certificate signing request, but now we want to sign it. In many cases, you might actually deliver that certificate signing request to some authority, third party or in-house authority that will actually process the CSR and generate the certificate. But here we're going to be taking on the certification authority role as well. So we need to create a certification authority. So let's create one. Okay. I'm not covering the OpenSSL CA command, which is a fancier CA than I'm going to show in this talk. It tracks the certificates that it's issued. It can generate CRLs. It can serve OCSP. But it's a lot more complicated than I have time for, but not quite complicated enough that in practice and larger enterprise deployments, you'd probably use something else. So I'm going to keep it simple and go with a very minimal CA. So let's generate a root CA certificate. So this is a slightly longer command, as you might notice. It takes 4 lines or 5 lines to write it out. We're going to use the OpenSSL rec command, which generates certificate signing requests. But in addition to, with -new saying, let's generate one, we're giving it one more flag, X.509, that causes it to immediately sign the certificate signing request as a certificate. So we'll never output a CSR, we'll output a certificate right away. We're specifying the output file to which it goes. We're generating a new key all in the same breath. The new key will be an elliptic curve key. It goes into the ca-key.pem file. And we're giving it the pkopt option to specify which elliptic curve and specifying the subject name, this time non-empty. So I'm putting all of these fields, C country equals Australia, state equals Victoria, and so on. But again, as I mentioned, so long as this subject is a well-formed, unique subject, it doesn't really matter that much what you put in there. Okay, we're also giving it an extension. We're saying it's a CA, and we're specifying the usual key usage for a certification authority, cert sign, and CRL sign. Okay, so what else do we want to say about this? That's probably enough for the moment. Homework, you'll typically create root CAs using RSA or ECD, not necessarily ECDSA. So try that instead. It's not any more difficult. Okay. Mini CA certificate. Once you've created it, let's take a look and see what's in there. I'm not showing all of the output, but I'm showing the essential parts. It's got an issuer. It's a copy of our subject name. They're the same, which is what you'd expect from a self-signed root CA. The issuer and the subject are the same. I asked for 20 years worth to the day in terms of duration for the key. So there it is. From November 4th of this year to 2044. May we all be around at 2044. And it's got X.509 subject key identifier and authority key identifier are identical. These were automatically generated. One has to ask to turn them off if one doesn't want them. And then it's got our requested basic constraints, and it's got the key usage that we asked for. Okay. Why stateless mini CA? As I mentioned, it's simple enough to cover. It's much easier to use if you're not in the business of publishing revocation lists or operating an OCSP service, because then all of that additional state that the OpenSSL CA utility maintains is just getting in the way. And there's no need to track any of that state. And as I mentioned before, in enterprise deployments, you may want a fancier CA than the one that comes with built in with OpenSSL. Okay, now that we have a CA private key and a CA certificate, by the way, the previous command, the CA private key, would have if you run it, it'll prompt you for a password to encrypt the key with. And you'll need to use the password again every time you use the key. So now that we're signing our CSR, the OpenSSL X.509 command can be used as a miniature CA. When you tell the OpenSSL X.509 command, read in a request, that automatically implies that what it's going to do with the request is want to sign it. So we say, okay, read in the request from the csr.pem file, output it to an EE certificate file, give it 90 days of validity from today, and use our cacrt.pem file as the certification authority certificate, use this particular CA key. That's the one that'll be password protected by default. There are ways to turn the password protection off, but for a CA, you often want if it's going to be used by people intermittently rather than in automation all the time, you probably want to password protect the key. I'm telling it to copy the extensions from the certificate signing request. After all, that's the essential content in there is those DNS names that we put into the CSR. We want them to appear in the certificate, so we have to copy them out from the CSR into the certificate. I'm being explicit about which extensions to include. So I'm saying copy extensions, but by the way, only the subject alternative name and the extended key usage are trusted to be valid in the CSR. I don't care what else it has in it. These are the two that I'm going to extract into the certificate. But in addition to copying the extensions, I can also say, well, add a couple more that I always want to add to end entity certificates. Basic constraint CA false, subject key identifier none. You don't need a subject key identifier in an end entity certificate. It's not going to be issued certificates to anybody else. So the subject key identifier is just bloated in there, so we're suppressing it. Okay. Inside the new EE certificate, let's take a look inside it. So I'm running a command to inspect it. I've given the cert opt option with lots of things you can read about in the documentation, but it suppresses the output of some of the fields, so we get to see only the ones that we're interested in. This time we see that the issuer is not empty. It contains the name of the certification authority certificate that I used. The validity, however, is only 90 days. That's what we asked for. So we go from November 4th to February 2nd of next year. The extensions are the ones I've copied and the ones that I added. So what we're seeing here is it's got the two DNS names, the extended key usage for being a web server. It's not a CA. It's got an authority key identifier to helping link it more precisely to the issuing CA certificate, and no subject key identifier because we asked for that to not happen. Okay, so this worked. All right. So now that we have our key in one file and a certificate created by the CA in another, I like to bundle them up together into a single file that I'll call the certificate chain file, but it contains not only the chain of certificates, but also the private key. And I'll talk about more about that why in a moment. Okay, so if we look at this chain file, so far the first command just copied the key into it. So our chain file just is another copy of the key, but it's got the correct permissions. Again, the pkey utility, when it creates key files, makes sure that they're not world readable. And then I'm appending the certificate to it. And in fact, not only the end entity certificate, but also the issuing CA certificate. In this case, it's the trust anchor, but often it'll be an intermediate CA. I'm not showing you examples that involve a complex CA chain, but it's easy enough to create intermediate issuing CA. And then you would really want to make sure that the chain file contains not only the entity, but also at least all the intermediates and optionally the trust anchor. So we're appending all the certificates in the right order to this file. And now if we look for these begin lines that start every PEM object in a PEM file, we'll see that this contains the private key. Our identity certificate presumably is the first one shown. And then we have the CA certificate second. All right. So why these combo files? So in these combo files, key and certificates are stored together. So it is much harder to end up with a mismatch in which an application ends up reading a key from one file and a certificate from another, and they don't correspond. Maybe it's an older key or an older certificate, and there's a mismatch and things go wrong. So if you keep them in the same file, they're less likely to get out of sync. Also, you can deliver the chain file atomically as one unit, again, writing it to a temporary file, moving it into place. And then servers that are carefully written might be able to be sure to read the same file for both without reopening or closing the file, avoiding race conditions. The PostFix email server that I'm actually one of the co-authors of gets this right and reads the chain file atomically. Other applications might nevertheless, even with a single file, open it once to read the certificate and open it again to read the key in some order. And then there's a possibility that the file gets replaced in the meanwhile if there's automation manipulating these files. So some of these applications have to be restarted or reloaded after certificates are rotated to make sure that they're in a consistent, clean state. Right. So, but that introduces race conditions that are best avoided. So I like to put everything in one file. Java servers don't use PEM files for their keys. They use something called Java key stores, or alternatively, as their key store, they can be told, you know what, read your keys from a PKCS 12 file. A PKCS 12 file is just one of these ASN1 encodings of a key and a complete certificate chain, all in one giant object. So it's similar to one of these combo files. So I like this philosophy of bundling all of these things together, and also makes it easy to convert back and forth for Java and other applications that want to consume the key and the certificate chain in one go. So, of course, it's up to the operator to then take care of careful atomic deployment, making sure that you don't need to restart processes because they're automatically seeing a consistent image of the key and the certs. Okay, let's inspect this chain file. Now that we're working with chain files that hold keys and certificates, let's try and look at the chain of certificates, so not the key. And counterintuitively, perhaps, the thing that best lets you look at a certificate chain is something called CRL to PKCS7, quite a mouthful, but it's designed to take certificate revocation lists in PEM form and convert them to a PKCS7 format that was originally designed for something called SMIME. It's an email security standard. But it's a way of packaging up a certificate chain into one ASN.1 object. So, but this command can be told, you know what, don't read a CRL, read a bunch of certificates instead, but output them as a single object. And then we can pipe that to OpenSSL PKCS7 that can interpret that object and print all of the certificates in one go. So unlike the X.509 command in OpenSSL, which reads only the first certificate in a PEM file, OpenSSL PKCS7 will read all of the PKCS7 objects. If it includes a chain, it'll output the data about all of the certificates in the chain. So what we're seeing here is a way of decoding a certificate file that may only contain these base 64 blobs and you don't know what each one means. Here we get to see the subject and issuer of all of the certificates. We could also see the certificate PEM encodings if we leave out the -no out. But more interestingly, we can do the same thing, but this time tell OpenSSL PKCS7 to actually print the certificates in text format, which will decode them. It would output lots and lots of fields describing each certificates. I'm showing a grep here only because I don't have enough room on the screen to show you the content of 2 certificates in one go. So here I'm showing that the -text option includes at least the issuer name, the subject name, and the before and after dates. So we get to see that my chain file has the 90-day certificate first, the one that expires in February 2nd of 25, and then has the 20-year certificate second, as expected. And they have the expected issuer and subject names. The subject name of the identity certificate is blank. So typically, you'd want to see more of the output. You'd pipe it to more or less or whatever, or even save it to a file. Up to you. Okay. So if we're really careful and want to perform sanity checks on our chain file, make sure that it's got the right certificate and the right key in it, we can run OpenSSL pkey to inspect the private key in the chain file, but we can ask, you know what, convert it to the public key and output it in dir form, and then compute a SHA-256 digest of this thing, hex encode it, and there it is, the hex encoding of our public key from the chain file. But we can do essentially the same thing, but this time extract the public key from the first certificate. So using the OpenSSL X.509 command, we're reading the first certificate in the chain file, and we're asking for the public key part of that certificate. And then we're asking OpenSSL pkey to take that thing, which is always going to come at us in PEM format, and convert it to dir format. So the second command there in the pipeline is its sole purpose is to convert PEM to dir. And then the third command computes the digest again, and we hex encode it. And again, we get the same value. When we get the same value out of both of these, we're sure that the public key part of the private key that's encoded in the chain is the same as the public key that ended up in the certificate. So the certificate is actually speaking about the right key. So here we can perform a visual comparison and see that these are identical. If you're scripting this, you can perform these sanity checks and compare these strings using your favorite tool to compare them. All right, so we can generate these PEM chains, but let's talk about using PKCS 12 files. They're useful for Java servers, or they're useful for delivery to end users. So what's a PKCS 12 file? So it's a password-protected key and chain container. It is used often for delivery of certificates to end users to install in their browsers or other applications if you're giving users a way of authenticating to some application using not passwords, but using private public key pairs. You might give them a PKCS 12 file. When you're delivering these by email or by other channels, you want to make sure that it's strongly protected by a password that's separately communicated over some other existing secure channel. On the other hand, when PKCS 12 files are used for a Java server process, there's nobody around to type the password for the Java server. It just needs to be able to read this PKCS 12 file from the disk and decrypt it. So the password can't itself be password protected. The turtles don't go all the way down. So really, the password may as well be some well-known string because it's going to be resident on the same machine as where the server is running. And the real protection of a PKCS 12 file used by a server is the operating system restricting who can read the file. So you can use something like not a secret for the password or whatever works for you. Anyway, right, PKCS 12 files. So let's convert our certificate chain that has the key, the identity certificate, and the issuing CA certificate all in one file. Let's convert it to PKCS 12. A note for anybody who has to interoperate with older versions of OpenSSL or older clients is that by default, since OpenSSL 3.0, which is quite a few years now, OpenSSL defaults to using AES-256 for encrypting the content or password protecting the content of PKCS 12 files. PBE stands for password-based encryption. So these are the algorithms used to encrypt the key and the certificates, and they default to AES-256 now, but they used to default to much older, already obsolete algorithms. And so if you need to interoperate with those tools, you either have to explicitly tell those tools to use the modern algorithms if they support them, or you might want to generate PKCS 12 files using the older password-based encryption algorithms. You can read about those in the documentation. Anyway, when we tell PKCS 12 command to export a chain, it will export everything that it finds there. It will export the private key, it will export the identity certificate, and it will export the chain. If we didn't have a single chain file, you'd have to provide separate arguments to say where the key is and where the identity certificate is and where the additional certificates are that go into the chain. But convenient thing about a chain is that it's all in one go, so we only need one argument. -in chain.pem takes care of everything. We must specify a password. PKCS 12 files are always password protected. This time it's not a secret thing, presumably for some sort of Java or other server where it will protect the file. It's not the password, but restrictions on who can read it. We can give it a friendly name, so when you later examine the PKCS12 file, you can determine what sort of thing it's supposed to hold. In this case, the certificate chain for www.example.net. And we get to write it to some output file. I'm calling it example.net.p12. So everything's imported, yeah. And note that the certificates are also password protected, not just the key. Maybe if you're giving this to a user, maybe there's some sensitive information about the user in the certificate naming or other details. So just in case, PKCS12 encrypts even the public certificates. Okay, now that we have a PKCS12 file, let's see if we can tear it apart and examine its content. So the PKCS12 command file, when it doesn't have -export, it's going to be reading the PKCS12 file, and -info is going to be decoding it in human-friendly form. So we're telling it, okay, decode the file for us. We're providing the password, the same, not a secret one, but this time we're telling it's the input password, not the output password. And we're saying, okay, output the content of the PKCS12 file, but skip the keys. Give us just the cert chain. Well, now that we have just the cert chain coming at us in PEM format with lots of other sort of stuff around it that will be ignored. We can pipe that to our friend CRL to PKCS7, but again, it's not a CRL, so we're telling it read the certificates from standard input, and PKCS7 print certs, great. We get to see our same chain coming at us with the empty subject for the identity certificate, the issuer, and then the self-signed issuer subject and issuer name. But it can, the chain could be more complicated, might have multiple CAs in it. But again, we have some confidence that this is the chain we were looking for. Homework item, once you see the next slide as well, you should be able to take the PKCS12 file and recreate the chain file from it and make sure that the chain file came out with the same content that went into the P12 file. Okay, so we've looked at the certificates in the PKCS12 file. We can also look at the key that's in the PKCS12 file. This time, I'm running PKCS12 again -info, but I'm saying no certs instead of no key, and no enc because it likes to always encrypt the private key. But I'm saying don't bother with that. And then again, we can take that private key and ask for its public part in dir format. Again, we can compute the digest, and what do you know? We see that we have the same public key digest as we had before. This covers the algorithm and the key content. So we're seeing that the right public key ended up as being the public key part of the private key. All right. We can again even do the same sort of thing, but extract the, with no keys, extract the certificate. And again, the public key part of the certificate, and again, convert it to dir, and again, digest and hex encode. And we're seeing that the PKCS12 file, the entity certificate in there, has the key that we expected. So again, in a script, you can verify that the key and the certificate match up by checking the hexadecimal encoding and making sure that they line up. Okay, we have certificates. We often want to check not just that the certificate is properly encoded and matching its own private key or public key, but that the certificate actually is properly signed by its issuing CAs. So let's do verification. So OpenSSL comes with a verify command that can check the signature chain on the certificate, making sure it was signed by its issuing CA, and if that CA is intermediate, that it's signed by its parent CA, checking all of the certificates and dates. So to check with the system trusted CAs plus additional CAs, you can run OpenSSL verify, give it optionally some additional trust anchors beyond the ones that are already installed in the system as trusted certification authorities. You can specify the untrusted option as additional certificates to build the chain with, because when a certificate chain has some intermediates in it, they might not be part of the certificate file you're looking at. The system trust store may have only the root CAs. The certificate you may want to check might have only the identity certificate, but the required intermediates may be nowhere to be found unless you provide them explicitly. So the -untrusted option lets you provide a PEM file with some additional certificates that may be necessary in order to link the certificate to the trust anchors that are trusted system-wide. We can specify a purpose for the certificate. It can be any of these SSL server, SSL client, and so on. I won't talk much about those. They're described in the docs. But it's important to specify a host name if it's a DNS certificate, so it can be sure that not only is the certificate properly signed, but it actually attests that it has the correct holder. So one of the subject alternative names would have to be www.example.net. And then we can specify one or more certificates to verify. Usually it's just one, but you can actually verify multiple certificates in one pass if you give multiple arguments there. Okay, verification example. We can, so let's be concrete and run this command. So we can say verify, and we're using our chain file as the CA file, because you might recall that we included the self-signed trust anchor that we generated, our mini CA, ended up in the chain file. We copied it in there. So we can use that as the additional sources of trust is our chain file itself. We can also specify it again as untrusted. If our chain file was longer, had additional intermediate CAs in it, then those would also be available to verify to use in constructing the chain. We can specify this purpose SSL server, which then implies that it'll look for an extended key usage of server auth or TLS web server authentication. If a key usage is specified, it would have to match this purpose, extended key usage. And we're specifying the verify host name of www.example.net, chain.pem, great. When we run it, oops, too far. When we run it, we see that verify reported the chain as being okay. That means it checked all the signatures, checked all the dates, checked the host name, checked the purpose, everything was satisfactory. And because I didn't show that I actually asked for it to show the chain. There's an additional option here, -show_chain, that isn't shown in the slide. Sorry about that. So I asked it to output the chain, and it outputs the identity certificate first at depth 0. It says in parentheses untrusted. This is not a bug, not a problem. What it's telling us is that it didn't come from the trust store. This is a certificate that we're verifying. So it's quite common and normal for the depth 0 certificate to be untrusted. In fact, often all but the last one are untrusted, right? They were used to construct the chain, but they weren't part of the system or CA file trust store. They were linked ultimately to the source of trust, which is here is a depth 1, is our mini CA. That's the one that's trusted. All the certificates that come before are verified. They are a priori untrusted, but now that they're verified, they're trusted by being signed by the last one that is. And if we look at the exit status of this command, 0 means success. So verification not only printed out chain okay, but returned an exit code that indicates that everything worked out. So right, we're host name purpose. Yep. So that's right. Homework. Check the other DNS send. There were 2 DNS names that we put into the certificate file. You can run the same command, make sure that both of them work. It's looking at the subject alternative names, and if either of them verifies, life is good. You can test a different purpose. You can try something other than SSL server and see that it'll probably be rejected because the certificate was narrowly defined just for being a TLS server. And you can try various other combinations and verify. If you leave out the CA file option, it probably won't verify because our mini CA probably isn't in your system-wide trust store. In this case, you can leave out untrusted because we only have no additional intermediate certificates to add. So even though I put the chain in there, it's redundant in this one example because our trust anchor is the direct signer of our identity certificate. Okay. Further reading. We have an OpenSSL guide to TLS that talks a bit about certificates and trust stores and all of that stuff. And I may give another talk about management of trust stores separately. That's a whole different topic related to X.509, but I simply don't have time in 40 minutes to cover everything. But you'll get a copy of the slides, so you don't have to try and write down this URL. When you come back early next week, you should be able to access the video of the talk and go over all the slides and look at the homework examples and play with them. All right, Q&A time.
Oh, sorry, I was muted. Awesome. Thank you so much, Victor, for a wonderful presentation. And as we stated before, this is now the Q&A session, so please feel free to use the Q&A box or raise your hand if you'd like to ask the question live. Some housekeeping I'm going to go over. As Victor said, this webinar is being recorded, and we will send you a follow-up email on Monday with both the webinar recording link as well as a copy of the slides. If you'd like to receive a copy of the slides sooner, please just email us at either feedback at, that's FEEDBACK at openssl.org, or marcom, that's MARCOM at openssl.org, and I'll be happy to get that over to you. And thank you so much, Victor, for a wonderful presentation. And thank you to our panelists as well, Neil Horman, Matt Caswell, and Hannah Anderson for being here with us. Thank you, everybody else, for taking the time out of your day. I know it's late for some of you for attending this webinar. As a reminder, this is
Please try the homework. Yeah, please go over these.
Please try the homework, and this is being recorded and will be sent out to everybody on Monday with a copy of the slides as well. So please stay tuned for that, and I hope everybody has a fantastic rest of their day.